All right, welcome back everyone. This is Calculus 2. So in this video, we are going to talk about 2.6 moments of center of mass. So far in chapter 2, we talk about, a lot of, benefit of using integral. So if you remember, it helps us to find out the area, volume, what else? Arc length, surface area, and force, and also mass. And then today we're going to find out the balance by using the integral concept 2.6. Okay, so as you see that chapter 2 is introducing many benefit of using integral in many different examples. In chapter 1 and 3, we already talked about how to take the integral, learning many different techniques. And chapter 2, we are going to apply this integral technique in finding area, volume, arc lengths in many different areas, okay? So let's take a look at the concept 2.6. So I'm gonna give you guys a little bit of, idea. So let's take a look at it. So if you remember when you were young age, you maybe play with seesaw. So in this image, we know that this is very general idea. If you have a heavy item, right, you're supposed to going down, right? And then if you're light, you're supposed to going up, right? So if you have a same weight, right? So your friends, I don't know, Charles is here, your friends is Kelly is here. Let's say they are on the same weight. And then you will imagine this kind of like situation. So if you have a same weight, right? This is a 20 kilogram, this is a 20 kilogram. To find out the balancing point, that's so let's say X bar. To find out the balancing point between two items, which they are same weight, you just need to have the same distance far away. And then you're going to find out the balancing point, right? So this is a very basic idea to find out the balancing point. But what if we have a different weight? Let's say you have 30 kilogram and here you have a 15 kilogram, right? And then in this time, you are definitely, having a difficult finding balancing point. So in this case, if you are moving up a little bit further to the center, if you're heavy, you're going to sit a little bit further. If you're light, you're going to sit a little bit. Sorry, if you're heavy, you're sitting in close to the balancing point. And then if you're light, you're going to sit a little bit further from the balancing point, right? So then they have a different distance. So you can maybe find out the balancing point, right? So mathematically, maybe we can think about this equation. Let's say you have weight M1, M2, and then M1 and M2, the weights are not equal to each other. And my goal is to find out the balancing point X bar. So let's say the distance between balancing point and M1, let's say this is X1, and the distance between M2 and balancing point, let's say that is X2. So mathematically, if you have this equation, M1 times the distance between X1 and X bar, which is X bar minus X1, that's the distance between M1 and balancing point. And then if you multiply M2, second weight times the distance, X bar minus X2, you can find out the balancing point, right? So mathematically, we can set up this equation from this observation. If you have the same weight, it's no problem. But if you have a different weight, you have to modify the distance back and forth to find out the balancing point. So therefore, this equation will be satisfied. M1 times D1, D2 specifically. This is M1 times X bar minus X1, that is equal to M2 times X bar minus X2, correct? Because this is exactly D1 and D2. So now I'm gonna keep developing this idea. So let me go down. So this is the same here. So we're gonna solve this equation. We have two different items. I want to find out the balancing point. So we know that m1 times x bar minus x1, this is d1, m2 times x bar minus x2, this is d2. So now I'm gonna use a distributive property. So that is gonna be m1 times x bar minus m1 times x1 equal to m2 times x2 minus m2 times x bar. Are you following? Now, I'm going to combining the like terms. So let me change the order. I'm going to move m2 x bar to the other side, and I'm going to move minus m1 x1 to the other side. So I can find out m1 x bar plus m2 x bar, because they're same common factor x bar. And then you can have the other side, m1 x1 plus m2 x2. So therefore, we can solve for what the x bar, because x bar now common factor, so that you're going to divide it by m1 and m2. We have x bar equal to m1 times x1 plus m2 times x2 divided by m1 plus m2. You can find out the balancing point. So this is how you're going to find out the balancing point between two different weights item. So we call the numerator, we call this is total moment. So more specifically, the capital M represent mass times its position, correct? We call this is a moment. And then the bottom little m, this is a sum of total mass. So in other words, moment divided by mass, you can find out the balancing point. Okay, so now let's expand this idea in the next level. What if I have a multiple? We have multiple items, and then all m1, m2, m3. Let's say you have infinite number of the item, and every item has, different weight. So same idea, you can still find out the balancing point, although you have many different items. Because m1 times x1, you're going to keep multiplying mass times its distance, mass times its position. So this is a total moment. And then you're going to divide it by all the summation of the moment. This is a total mass. So if you have total moment divided by total mass, you can find out the balancing point of multiple items. Does it make sense? So this is a very similar, like the Riemann sum we've been talking about since beginning of the semester. So to find out the total moment, you're gonna have mass times its position from 1 to n. So this is a summation. You will find out the capital M. Same thing, you're gonna adding all the summation of the total mass. That's gonna be little m. So you're gonna find out the capital M and little m. You're gonna divide it. That's gonna be the total, the balancing points of the multiple items. Does it make sense to you? So from this observation, we are able to find out the balancing points. And I will show you the example more and more. So hopefully this concept, it's understandable. So let's take a look at the following question. Are you guys okay with that? So let me go down slowly. So, let's think about this question. So the M1, this item, 30 kilogram, and then it's a left side, it's far away to the left side, 2 meters away, right? So if I imagine, I don't know what the balancing point, but M1 is here. This is M1, and then this is a 30 kilogram, and then to the left side, -2 meter. And then I have M2, this is a 5 kilogram. Here, M2, much heavier. And then this is a 3 meter away from the balancing point to the right side. And you have another one, M3. This is a 10 kilogram and 6 meter away from the balancing point to the right. And last one, 15 kilogram, it's pretty heavy. And then this is to the left side, 3 units away from the balancing point. So to make the, to find out the balancing point, these are the given information. I don't want to, this one is going down or this one is going up. I just want to find out the balancing point. Nothing is going up and down, just we're going to find out the balancing point. Where is it, right? So we know a couple information. If you know the total moment and total mass, you can divide it. That's how you're going to find out the balancing point. So let's write it step by step. We call the balancing point, or we call the center of mass. That's the same language. Mathematically, that's X bar. We are trying to find out the X bar, that is a capital M divided by little m. So capital M will be found the summation from 1 mass times its position. So which means we have 4 different items, correct? So it is going to be M1, X1 plus M2, X2 plus M3, X3 plus M4, X4. So mathematically, first one, 30 kilogram times -2, M2, 5 times 3, 10 times 6, 15 times -3. So if you calculate it, -60, +60 cancel, 15, -45, the -30, this is the total moment. So this is a capital M. This is total moment. Are you okay with that? So we got the capital M. Let's find out the little m. So little m is only the summation of the total, all the mass of the item. So n, if you go up, that was the formula. So I'm going to highlight it one more time. So we're going to find out mi. So which is M1 plus M2 plus M3 plus M4. So if we're adding 30 plus 5 plus 10 plus 15, so that is going to be 60. So we got this is a total mass. So therefore, X bar equal to capital M divided by little m. So we have -30 divided by 60. I have -1/2. So what does it mean? We call this is the balancing point. So I'm going to write a couple language. This means the center of mass, or depending on the textbook, some textbooks say this is a centroid, or this is the balancing point. So these are the centroid is located 1/2 meter to the left from the origin. So that's your center of mass balancing point, and that's the balancing point. So that's how you're going to find out so when you're holding, when you're here, nothing is going to be up and down. They're exactly on the linear line. Okay. So that's how you can find out the centroid. Okay. So that's a pretty much like straightforward question. So let me give you a little bit challenging idea. What if we have the same situation in 2-dimensional space? So this is a 1-dimensional space, right? Which means everything is on the one line, x-axis. But what if I'm thinking to find out the balancing point in 2-dimensional space? So you are going to find out 2 balancing points. One is on the x-axis, another one is on the y-axis, right? So let's say you have a multiple, items on the 2-dimensional space. So let's say M1 this, you have x1 and y1 at that position. M2 is gonna be x2, y2. M3 is x3, y3. So let's say you have a couple, items in two-dimensional space, and then to describe its position, you're gonna use the coordinate points x1, y1, or x2, y2, right? It's the same thing. To find out the balancing point, x bar, y bar, you're gonna need the total moments divided by total mass. But in this time, you're gonna find out the total moment and total mass with respect to x and y separately. So what I'm saying is how to find out the mx. This is a total moment. This is a total moment with respect to x variable. So in this time we call, so x, you have a multiple, so this is a far away, this m1 is far away, on the x-axis to the left. We don't know how much unit, but this is the distance, and this is the distance, and that is a distance. So in this case, to find out mx, this is the formula. We used to have multiply its position, but in this time, you're gonna multiply opposite, okay? Opposite position. So same thing for my. So this is going to be total moment of x, y respectively. Capital mx, you're gonna find out the total moments with respect to x variable. In that case, you're gonna multiply. Anyway, you're gonna mass times its y's position. And then for the y moments, you're gonna multiply x position. So that's the only different thing. And then once you have, m, y, and mx, you're gonna find out the balancing point. So this is a little bit tricky question because many people think, oh, x bar is gonna be mx divided m, but it's an opposite. You're gonna find out m total moments of y, then divided by m, give you x bar. And then total moments with respect to x divided by m, you're gonna get the y bar, okay? So think about it, this is opposite variable so that many people make a confusion, but just be careful because it is a two-dimensional space, okay? Because it is a two-dimensional space. If you are talking about, y variable, so this is, if I go back to this image, you are describing m1. So y is vertically, this is the distance with respect to y. This is the distance with respect to y. This is distance with respect to y. But actually, it's also far away. It's also, there's a difference in terms of x variable. This is the amount of the x variable, x variable, x variable. So what I'm saying is when you're describing the position of y, actually we are using the x-axis, right? When you are actually, describing the distance in terms of the x variable, you're actually talking about the y distance. So it's a little bit, abstract thinking, but what I'm saying is just use the opposite variable to find out the total moments of each x and y, okay? So mx, you're gonna find out mass times its position, but its position is gonna be y. Same thing, my. To find out the total moment of y, you're gonna multiply the opposite position of x. So then this is the final formula because of the balancing point, x bar, y bar. Anyway, capital M divided by M, but x bar, you're gonna use y bar, you're gonna use x, okay? So let me show you the example so you can see what's going on. So let me go down a little bit slowly. So keep in mind that formula. So I'm gonna make us a little bit of star. So we're gonna find out the centroid, the balancing point of three following items. So this is a two-dimensional space because I do see coordinate points. So we know to find out the centroid, or we call, balancing point, or we call the center of mass, X bar, Y bar equal to, be careful, X bar, moment Y over mass, and then moment X over M. So we're gonna find out that information. Let's find out the total mass first, little m. This is total mass. So total mass is given 2, 6, 4. So I'm gonna 2 plus 6 plus 4, that is gonna be 12. So this is going to be total mass, correct? And then we're gonna find out the capital mx. What does it mean? This is a total moment with respect to x-axis. So we know the formula. It is going to be n mi, and be careful, you're going to multiply yi, correct? So that means you're going to do m1 y1, m2 y2. Oopsie, I need a little bit of space. And then m3 y3. So if you calculate it, what you're going to get? That means 2 times 3, 6 times 1, 4 times -2. So if you calculate it, 4 is the total moment with respect to y. Okay. We're going to do one more thing. My total moment with respect to y-axis. So that is going to be, we know, opposite mi times xi, correct? So let me change the color. That means not y, it's going to be xi. So m1 times x1, m2 times x2, m3 times x3. So what happened? 2 times a -1, 6 times 1, 4 times 2. So if you calculate it, I got 12. So that is total moments with respect to y. So we're going to find out equal to, we got it, my is going to be 12, right? This is my, 12 over 12, comma, 4 over 12. We can simplify. So that is going to be 1 comma 1 over 3. So what is your answer? The centroid of those 3 items coordinates, the centroid of those 3 items located are, or I'm going to say is located where? At 1 comma 1 over 3. That's your balancing point, centroid. Does it make sense? So I introduced how to find out the balancing point in 2-dimensional space. All right, and then the previous question, we were able to find out the balancing point in 1-dimensional space because everything is on the same line. This is, we have 2 coordinate points. So to describe its position, we have to describe x coordinate and y coordinate. So this is 2-dimensional balancing point. So it's getting better and better. Okay, I'm gonna give you one more concept in terms of 2.6. What if we have, it's still in 2 dimension, but what if we have like a very, ugly, geometric shape, and I want to find out the balancing point. So for example, I'm going to go down slowly. So we have a concept of lamina, which means it's a very thin, like a paper, you can think about it. It could be thin tissue. It could be a, surface area of the basketball. So let's say, you want to find out the balancing point. Let's say I have a basketball, right? So Michael Jordan, he's so good at, holding the basketball by using his one finger because he might know the balancing point, isn't it? So, that's actually kind of like three-dimensional space basketball. And then we have a multiple infinite points inside of the basketball. We want to find out the balancing point to hold it. So you can think about it as a lamina shape. So how to find out the centroid of the, thin plate or napkin. Let's say you have a napkin, I want to hold it, or you have a paper, you want to hold it, you have a basketball, you want to hold it. How would you be able to find out the balancing point? In that case, there is a density, okay? Because there's a little like a weight, basketball, it has a weight. So let's say there's a density, okay? So in that case, a little bit of a modification. It's the same thing. We're going to find out the centroid. Anyway, to find out the balancing point, it's a capital M over N. Always a total moment divided by total mass. But let's consider there is a density of the item, okay? It's not just like position times the mass. There's a density involved. So in that case, if you want to find out the total mass of lamina, so this is going to be total mass of lamina shape, then you're going to use the integral, and then there's a density. So because that item has a density, so P represent density. So you have a density times whatever the given function. So you have, let's say this is the function. When you're rotated, they're going to create like this, whole shape. I want to hold it by finding the balancing point. So this item has a density. And then to find out this shape, there's a function is a given. So there's a, distance between A and B. So by utilizing the integral, we can find out the area. So from A to B, with the F function, this is area, but we have a density. Okay, so once you multiply density, it is going to be the total mass of lamina shape. Does it make sense? So this is the formula to find out the total mass of lamina, which is the bottom work. Now I want to find out the total moment. Still, we have X and Y in this function because there's input and output. So mx, right? With respect to X variable, this is total. I'm going to write it total moment with respect to X variable. Then you're gonna utilize this formula. So A to B, f of X square, and then density function divided by 2. I know it's a little bit ugly, but that's what it is. It's a given function. And then the next one, this is a total moment with respect to Y variable, right? So this is going to be P times density from A to B, X times f of X, because it's going to be kind of like a circle shape in terms of the Y variable, okay? So therefore, by taking the integral to find out each total mass and total moment with respect to X and Y, at the end, we're going to find out this formula always. This is still two-dimensional space. To find out X bar, you're going to use my divided by m. Y bar is going to be mx divided by n. So this is going to be given formula. So think about it. I'm going to get rid of it. So this is how you're going to find out the centroid of the thin plate, lamina shape. Okay, so I'm gonna use this information to solve the following question. Okay, so you guys gonna organize all the formula, right? We have been introducing many different formulas depending on the topic. So now this is another edition. Okay, so let me just write one more time. So we're gonna do number 3. Let me write all the formula one more time. So the mass, total mass, P times density A to B, Fx times dx, this is total mass. And I know mx is going to be P over 2 from a to b, f of x square dx, we're going to take the derivative, integral, and my, as you see, that was what? P times from a to b, x times f of x dx. So once you find out those three information, and then x bar will be my over m, y bar will be mx over m. So you're going to utilize this formula to solve the following question. Okay, let R, this is the region bounded above by the graph. We have a function f of x equal to radical x, and below by the x-axis from 0 to 1, 0 to 4. Find the centroid. So they're going to, create a shape, something like this. I want to hold this shape by finding the balancing point. So let's do step by step. And then density function is given equal to 1. So step 1, let's find out the total mass of the lamina. This is a lamina shape. So that is going to be m equal to p times a to b, f of x times dx. So p is a 1 from 0 to 4, and then our function is a radical x dx. Am I correct? So that means 1 it's the same thing. So 0 to 4, radical x is a half exponent dx. Now you're going to take the integral x 1 over 2 plus 1 divided by 3 over 2 from 0 to 1. Yeah. I'm going to flip this one. So that would be 2 over 3 x to the 3 over 2 from 0 to 1. And then we're going to subtract from 1 to 0. So 2 over 3, 1 to 3 over 2, and whatever it's going to be 0. So if you see that, the answer should be, I have a little bit of typo. This is a 4, 0 to 4. So I have to plug in 4, not the 1. So 4. So if you calculate this one, that is going to be 16 over 3. Gotcha. This is a total mass of this lamina shape. Are you following? Okay, we good. Keep going. Let's find out the total moment with respect to x variable on x-axis. So the formula is set right there. mx equal to p over 2 a to b f of x second power dx. So p is a given, so 1 over 2 from 0 to 4 right there. And then the function is radical x to the second power dx. So we know the second power in radical cancel. So basically we have 1 over 2 from 0 to 4 x dx. So I can take the integral 1 over 2 x 1 plus 1 divided by 2 from 0 to 4. So that means 1 over 4 x to the second from 0 to 4. So if you calculate it, this is 1 over 4, 4 to the second minus 0, isn't it? So let me just minimize it. So minus 0, so we have 4 here. This is a total moment with respect to x-axis. Sounds okay? Keep going. 3. We're going to find out total moment with respect to y-axis. So the formula said right there, p times a to b, x times f of x dx. So p is 1, 0 to 4, x times radical x dx. I can combining 0 to 4, x times x to the half exponent. So again, that is a 0 to 4, x to the 1 plus 1 over 2, 3 over 2 dx, correct? Now we're going to take the integral. So x to the 3 over 2 plus 1 divided by 5 over 2 from 0 to 4. And then we're going to bring up 2 over 5, x to the 5 over 2 from 0 to 4. So once you calculate it, 2 over 5, 4 to the 5 over 2 minus 0. So once you calculate this part, that would be 64 over 5. So this is total moment with respect to y-axis. So you guys did a good job. So let me just get rid of that paper. I need a paper here. Okay, so now we have all the three information. So what is the centroid? The centroid of the lamina, x bar, y bar will be my over m, comma, mx over m, correct? So you have all the information right there, right there, right there. So my, 64 over 5 over 16 over 3, that's a total moment over total mass. And then comma 4 over 16 over 3. So we're going to simplify this ugly fraction. So just, you know, what does it mean? 64 over 5 divided by 16 over 3. You guys know KFC, Kentucky Chicken Fried. Or keep change, flip over. So 64 over 5 times 3 over 16. So it'll be 12 over 5 and then 3 over 4. So that's your balancing point of this lamina shape. Pretty straightforward question, okay? So this is a third concept. If you have your item has a density because of the weight and because of the shape, there's a density is a given, then we're gonna use, this is a lamina, and then you're gonna find out the total moment and mass using this formula, okay? All right, I'm gonna do one last question, a little bit complicated. So in this concept, we had only one given function. Ooh, what if I'm giving you two functions and let's find the centroid balancing point. So here we go. So same concept. You have two functions going on. So let's say I have this two function, f of x and gx. And then from A to B, I'm not talking about the area, I'm talking about the balancing point. So when you have rotate this two function, either y or x-axis, they're gonna have some shape, right? And then I wanna hold it by finding the balancing point. So same thing, this is the area formula, the larger area minus a smaller area, right? And then you're gonna multiply density, that's it. That's gonna give you the total mass of the lamina with two functions. So I'm going to highlight it, centroid. This is a balancing point. This is a centroid. When you have lamina of lamina with the two functions. So this is going to be the lamina total mass, correct? And then what do you guys think? Same formula from the one. So this is bracket. So same thing, mx is going to be p over 2, and then large square minus a smaller square from A to B. Same thing from the one function given. My, p times x, then subtract f and minus g. You always need to check which one is a higher function. So f and g, you have to decide it then. Then x bar, balancing point, my divided by m, mx divided by m, that's the balancing point of lamina with two given function. Are you guys okay? So same thing. This is a total moment with x variable. This is a total moment with y variable. So that it's the same formula as you see here. Just so we have two functions. So the differences. So we're gonna do this work, okay? So keep in mind, those are three. Let's do this function. We have a two function f and g. They want you to find out the centroid balancing point, the density given as 1, which is a good. And then f is this and g is that function. Check it out, which one is higher? So first of all, they didn't give us any a to b. So first, to find a to b, we're gonna say f of x equal to g of x, correct? So 1 minus x squared equal to x minus 1. So that minus x second, I'm gonna move everything to the other side. So minus plus 1 equal to 0, right? I subtract x on both sides. I'm adding up 1 on both sides. So minus x plus 2 equal to 0. I'm going to divide it by negative everywhere. So x second plus x minus 2 equal to 0. Now you can find out the binomial factor, x plus 2, x minus 1, which means x equal to negative 1, x equal to 1. What happened? This is a negative 2. This is b 1. So we have the balance, the intersected. We found out the intersected point between, which is negative 2 to 1 on x-axis. All right, now we have pretty much every information, correct? So you have density function, you have a to b, and then you need to decide which function is higher between this. Always, what happened? The f function is a higher, right? They're always a higher, height. So that f of x we check is a higher height. So that we can subtract from the f function. We also check this too. So we're gonna find out the 3 information. So I'm going to copy this because what we have, I'm gonna actually not the copy, I'm gonna just write everything. So we have to find out first total mass of lamina in this time between 2 functions, right? So we know the formula P a to b, the large minus smaller height function dx. So P is given 1, a to b, negative 2 to 1. What is f? 1 minus x second minus g x minus 1 dx. So I'm going to simplify as much as I can. So this means negative 2 to 1, 1 minus x second. You're going to do the distributive property, negative x plus 1 dx. So take the integral, then x minus x third over 3, x second over 2 plus x from negative 2 to 1. So we are going to subtract from large to small. Let me minimize, and then I'm going to bring this one to here. So then what happened? 1 minus 1 over 3 minus 1 over 2 plus 1 minus 0. Actually minus 2. So minus 2. What happened? We are going to, actually, you know what? We can simplify. We can combine in like term. X plus x, we can combine in like term. So minus x to the third over 3 minus x to the second over 2 plus 2x from negative 2 to 1. Gotcha. So that would be, if you're plugging in 1 first, so negative 1 over 3 minus 1 over 2 plus 2. This is capital letter 1. And minus, when you're plugging in negative 3, negative 2, so that it's going to be that. Negative 2 to the second over 2 plus 2 times negative 2. So this is capital F of 2. So you can plugging in that equation to decimal. You should get 9 over 2. This is your mass, total mass. How you feel? You good? So this is going to be total mass of lamina between 2 functions. We are not done yet. We're going to find out the total moments. Keep going. 2 total moment of lamina respect to x-axis. And then this is between two functions, right? So the formula was mx equal to p over 2 from a to b, large function second power minus smaller function second power dx. So density is given 1 over 2 from, we have a to b, which is a negative 2 to 1. F of x, what was it? 1 minus x to the second minus g function. That was x minus 1 to the second, and you're going to take the integral. We have to expand it, 1 over 2, negative 2 to 1. Expand everything. So 1 minus 2x second, x to the 4, minus x second, minus 2x plus 1, and dx. Keep going, 1 over 2, negative 2 to 1, 1 minus 2x second, x to the 4. You're going to do all the distributive property with invisible negative 1. So negative x second plus 2x minus 1 dx. So here 1 and 1 cancel. Nothing is a cancel. So basically we're going to get 1 over 2, negative 2 to 1, large exponent 4, and then negative 2x, negative x second minus 3x second plus 2x and dx. So when you take the integral, 1 over 2, x to the 5th over 5, 3x to the 3rd over 3, 2x second over 2 from negative 2 to 1. Gotcha, gotcha. Okay, now we're going to subtract 1 over 2 when you're plugging in 1. So you should get this. Minus 1 over 2, negative 2 to the 5th over 5, 3 times negative 2 to the 3rd, plus 2, negative 2 to the 2nd over 2. So this is 1, this is negative 2. Again, this is a complicated fraction. You can type this in decimal so they can find out negative 27 over 10. So check this one. This is a total moment of lamina with respect to x between two functions. Awesome, we're almost done. One last thing, you know what that is. Total moment of lamina with respect to y variable between two functions. So let's take a look at it. So the formula my, p times a to b, and then x, don't forget that x times f of x minus gx. And then p is 1, we have negative 2 to 1. F of function was 1 minus x second, the g function x minus 1, and dx. So negative 2 to 1, you can simplify distributive property, negative x plus 1 dx. Okay, 1 plus 1, that's a combining like term. I believe that is going to be 2. So I forgot this one, the x. You see that? So I'm going to multiply here x. So that's where many people make a mistake. I told you, I also made a mistake. So we have to multiply x one more time. So that is going to be negative 2 to 1. Distributive property, x minus x to the second, x to the 3rd, and minus x to the 2nd plus x dx. Now you can take the integral. X 2 over 2, x 4 over 4, x 3rd over 3, x 2nd over 2 from negative 2 to 1. Awesome, we are doing good job. And then subtract 1 over 2, 1 over 4, 1 over 3 when x equal to 1. This one minus the complicate one when you subtract the negative 2 part. So negative 2 to the 2nd over 2, negative 2 to the 4 over 4, negative 2 to the third over 3, negative 2 to the second over 2. Anyway, you're gonna use a decimal because it's a complicated fraction. It should be about negative 9 over 4. This is a total moment of lamina. So what is your final answer? We are not done yet. We're gonna find out the centroid. Centroid of lamina between two functions set x bar, y bar equal to my over m, mx over m. So we have all the information right there. So we have to plugging in, what is it? Negative 9 over 4 over 9 over 2, comma, negative 27 over 10 divided by 9 over 2. So this is going to be the centroid. Please simplify. That is going to be negative 1 over 2, comma, negative 3 over 5. That's the centroid of lamina when you have two different functions. So please check this information. Okay. So we finished 2.5 here, 2.6 actually. Check all the different formula, one-dimensional centroid, just simple two-dimensional centroid, two-dimensional and lamina shape centroid, two-dimension or three-dimension, but anyway, lamina, actually two-dimensional lamina with, this is with one function. And we talk about two functions as well. So you can find out, I'm gonna make a little bit here. You can find out the balancing point centroid. So there's each formula, total moment, total moment with respect to x and y, and total mass. Check each formula, you can complete 2.6. Okay, so we finish all the practices and I try to my best to give you all the example as much as I can. So you can finish quiz 2.6. If you have any question, we have a discussion board. It's very active. So keep going. And if you have any further question, email me anytime. Okay, so I will stop recording at this moment. We'll see you in the next video. Thank you, everyone. Bye-bye.